Hello there, physics class. I hope you're having a good day and we're ready to embark on chapter 10 here and get going. What I need you to do is make sure that you are taking notes today. I don't have the assignments for you yet posted, but they will be. I'll be sending you some documents for that so that you can be working. Hopefully you've got your book so you can start working on practice problems and whatnot all along, and that's just how we're going to handle that. All right, so today we're going to start talking about energy. And energy is really anything that has the ability to cause a change in itself or its environment. So therefore, energy can be stored. Energy can be currently in the process of changing itself or its environment. Energy can be found in all kinds of things. It can be stored because of a position, because of gravity, or it can be something that's moving, so it possesses energy because it can cause a change, or it can be even stored up chemically, or even in the nucleus of an atom. There's all kinds of energy, but we're going to focus right now on kinetic energy, and kinetic energy being the energy of motion, because anything that's in motion does have the ability to cause a change in itself or its environment. All right, so imagine, you've got something flying through the air. If it hits something, it's causing a change in its environment. Or even if it breaks into pieces, it's causing a change in itself if it hits something. So you've got the kinetic energy or energy of motion, and our calculation for that is based on its mass and how fast it's going. So the faster something is going, the more kinetic energy it has. Or if you have a larger object, the more kinetic energy it'll have if it was going the same speed as a smaller object. So it kind of works like momentum, except for when we have momentum, the mass and velocity count for the same amount of it, but in the kinetic energy, the velocity ends up being squared, so it carries a little bit more of the weight of that. So when we think about our units for these things, mass is kilograms and velocity is meters per second. So it's really kilogram meter squared per second squared. But we have another unit, and it's called a joule. It's with a capital J. That is a shorthand way of writing a kilogram meters squared per second squared. So we have this new unit, a joule. Joule coming from James Prescott Joule, a scientist. And so our words that go with them are work is going to also equal force times distance. That's a little bit different than kinetic energy, but it's also very, very closely related to energy. Okay, so kinetic energy, the energy of motion, closely related with the same unit for this idea of something called work. Now, work has to do with how much force was applied and the distance through which that thing moved. So work meaning force times distance. Force we know is measured in newtons, which is a kilogram meter per second squared, and you multiply that times another meter, and you end up with a kilogram meters squared per second squared, which is what we just said a minute ago, which is the unit for joules. So work and energy so closely related, because what can happen is that thing with kinetic energy can do work or cause something to move. So as they're related, what we can think about is that 1 joule of energy can do 1 joule of work. So they're the same thing. A Newton meter is the same as a kilogram meters squared per second squared. And that leads us to something called the work energy theorem that says if the kinetic energy changes, that equals the amount of work that was done. So the change in kinetic energy equals the amount of work. Now, this whole idea of work with the force and the distance, if you're considering work being done by something, Okay, you're only considering the work if the force and the distance are in the same direction, or at least along the same line. They can be in opposite directions, but along the same line. You can have positive work or negative work. But if you're considering possibly like carrying something around, okay, you're carrying something around, you're putting your force, and you're thinking about what the force of your arms are that's pushing up, but you're just walking back and forth sideways. The force from the bottom of your hand is not doing work as you're pushing up on that object, because your force is up, but the distance you're going is sideways. So those two things don't work out. So you're not doing work with the bottom of your hand if you're holding something, if you're just holding it at that same level, because it's not going up and down. The force and the distance are in different directions. So you've just got to work, figure out what the agent of force is, and figure out in your question whether you're considering work to have been done or work not to have been done. So let's take a look at some examples. We have a 105-gram hockey puck and sliding across the ice, and a player exerts a constant 4.5 newtons of force over a distance of 0.15 meters. Okay, so he's got a force and he's got a distance. So we can answer the question first: how much work does the player do on the puck? He's pushing it in the same direction it's moving, so we've got force and distance, so it's simply a matter of multiplying your force times your distance, your 4.5 times your 0.15, and getting an answer. And you're all capable of doing that calculation. 0.675, here's our new unit of joules. Now the second question, what's the change in the puck's energy? The puck should say puck's kinetic energy. The change in the puck's kinetic energy is actually the same amount as the amount of work done, because they mean the same thing. Remember we said that delta K equals work. Okay, so the puck, the player with his hockey stick, is doing work on the puck, and as he's doing that, applying that force and the distance, we could have a change in the kinetic energy. So what he's doing is he's putting that energy into the puck. Now for this particular moment we're neglecting friction, so all of his work that he's doing is actually causing the puck to go faster and change its kinetic energy. And yes, we know that friction exists, but for right now we're just kind of pulling that out of our discussion. You can also do work as you're opposing gravity, or gravity itself can do work. So that's up and down motion, up and down directions. So if you're trying to lift perhaps something, 102 kilogram scooter, that would be quite a heavy thing just to be lifting up into the back of your pickup truck. And the bed of the truck, in other words, the part that you put the stuff into, is 0.8 meters from the ground. And if you want to find out how much work you do to lift it into the truck, we can think about our work equation, force times distance. And we have a nice distance involved here, but what we're missing is the force. We have a mass, but we don't have a force. So before I say it, think for a second, or pause it so that you can think, and figure out how would I get a force out of this? And you have to think, well, the force that you have to overcome is the force of gravity. So if you remember, we calculate how much force because of gravity, or its weight, by taking mass times little g, the acceleration because of gravity. So you're taking your 102 kilograms times 9.8 meters per second squared, and we would end up with 999.6 newtons. Okay, so newtons being the force unit. Remember, all of our forces are measured in newtons. We have this number now, that's our force, and our distance applied is 0.8. And like I said, you're perfectly capable of pushing the buttons, and so we have about 800 joules of energy that was spent in order to lift that item up into the truck. All right, and so we could ask also other questions regarding that, but the first beginning part is just to be able to calculate the work. And the work was done by you. You were the one that did the lifting of the moving of that object to that height. Okay, now we've got another scenario. In this case, you aren't doing the work, although you did have to probably do the work to carry the ball up to the top of the stairs in the first place. But this is asking how much work is done on the bowling ball that's being dropped to the ground. How much work is being done by gravity. You let go of that thing, and so you've got gravity pulling it down. And once again, the force because of gravity is another way of saying weight. So we do need to figure that out. There's your 3.9 times your standard 9.8. We are assuming that this is on Earth at sea level rather than being somewhere else on the moon or whatever. That would be a whole different value for little g. And we have our force being 38 newtons, and that is applied over the 5 meters, which ultimately gives you 190 joules. And you can imagine as that bowling ball drops, it's gaining kinetic energy. So what's happening is that force applied over that distance would transfer 190 joules into the motion of that bowling ball. We need to bring back our remembrance of prefixes here as something, and I ran out of creativity, so it's just something, whatever it is, was lifted 4.3 meters, and in order to do that, the amount of energy was 9 kilojoules of work. So if you are talking about 9 kilojoules of work, remember kilo means 1,000, so it's 9,000 joules. So our question is what the mass of the object is. So once again, we need to consider force times distance. 9,000 joules, force times 4.3. Solve for force, but we still haven't answered the question as far as what the mass is. So hopefully you're already thinking about what we talked about a little bit ago, is that this is the force that was used to do that, but that's the same as mass times little g gravity. So force equals mass times 9.8. Divide that out and you have the mass of this object was 214 kilograms. So a pretty good sized thing that was being lifted with those 9,000 joules of energy. All right, our next question deals with pushing a lawnmower. You can imagine pushing a lawnmower and you're pushing it at an angle. And so the angle on the handle is down this way. This is your lawnmower. You've got your mower down here. Your hands are up here. You're pushing it with 300 newtons of force. But the handle isn't, your handle on a lawnmower isn't going to be straight across. The handle on the lawnmower is at a 31-degree angle. And you want to move this lawnmower as the lawnmower is going across 15 meters. And we want to find out how much work is done in that scenario for that, how much work in this direction. Now keep in mind when you're pushing with this force, you're pushing not just sideways, you're pushing sideways and down. So your force is kind of broken up into its two components. But we're thinking about how much is causing the sideways motion, so the force and the distance being in the same direction, how much is going into the sideways motion of this lawnmower. So how much work was done is only going to consider the x component of that work. So remember sine, cosine, tangent. Cosine is adjacent over hypotenuse, just like we've been doing. We've done this so many times. Adjacent over hypotenuse, cosine of 31, x over 320 newtons. In order to solve it, just move that over. Make sure your calculator is set to degrees rather than radians, especially those that are also taking Algebra 3, because we're in radians now in Algebra 3. So 320 cosine 31, we get about 274 newtons. And the object is moving to the right in this particular picture, so that is our amount of the force needed. It's moving the 15 meters. So let me just do this. Pardon my handwriting there. There we go. It's moving the 15 meters. It's hard to write on this thing sometimes. Force times distance, 274 times 15, and that gives you a little over 4,000 joules of energy as far as the work that was done on the sideways part of it. It doesn't mean that you weren't also pushing downwards. So what you're doing is actually more than just pushing the lawnmower forward, but we're just talking about the sideways motion in this case. So when you're asked to find how much work is done, there's a little shortcut to that. You don't have to actually draw out the picture. You can use the formula. And the formula is the work is the angle between the force and the displacement you use for theta. And you can use this formula right here. Whoops, I was trying to neaten that up, but that didn't work very well. The angle between the force and displacement would be theta. And you have an angle between your force and displacement. So work equals force times distance times the cosine of theta. If there's no angle, it's just force times distance. It's just that if you have that force coming in at an angle, kind of like when we were talking about torque and we were trying to figure out the lever arm and we had to consider angles in there. This formula is, though, just a little bit easier than that, so we can bring it down to being that much. It says displacement. I'm going to type that in for you. How about that? There we go. So we're going to say work, and you're writing it down anyway, so this doesn't slow you down too much. Work when you have an angle between force and displacement. Okay, so that's much better. I can neaten that up a little bit for you. It was really good to see some of your faces when we got together on the Zoom conference. I hope that you're all doing really well on your group project that you were to be turning in by the end of today, but as we move forward, this is the beginning phase of it. This week, you're also going to be getting a good jump on this chapter 10. I will expect us to be meeting together, as I said, Friday on a Zoom conference real quick to run through what we will do as a lab. You'll be receiving some materials probably by the end of the day tomorrow, just to help you get organized and think things through a little bit. All right, that's good, and that's all I've got for you today. Have a really great, wonderful, blessed day, and I hope to see you soon.